Yes, so let us start the session. Yeah, so let us start this session. Let me share my screen. In our previous sessions, we were discussing about um adders, subtractors, and implementing subtractor using a half adder and all. And we have completed those particular topics. Let me show you what we have discussed so far. And we will start with comparators today, right? So we have basically started with developing full adder using half subtractor and half subtractor, full subtractor using half adder and all these circuits we have implemented. And yeah, and also we have implemented full adder come subtractor circuit also we have discussed in our previous sessions, right? Now in this particular session, let us start with implementing first about multiplier. So let us see how to implement a simple multiplier now. So let's say if I'm going to have a 2-bit number and if I want to multiply that particular 2-bit number where my e is equal to a1 a0 and I'm going to have b, which is nothing but b1 b0. This is the 2-bit number which I'm going to have. And if I need to multiply this two numbers, now how we are going to multiply, let us have a look into it. So let's say this is my a1 and a0 and this is my value a, and this is my b1 and b0, this is my b, right? Now if I'm going to multiply these two numbers, so what is that I'm going to have? I'm going to have over here A0 and B0 and A1 B0 and A0 B1 and A1 B1. And I'm going to add this so that I'm going to have A0 B0 and I'm going to add this so that I'm going to get some particular sum. Let's say it is S1. Okay. And I'm also going to get one carry. This is, let's say, C1. So I'm going to add this carry C1 with the other uh, product term. Then I'm going to get something known as S2. Okay. So this is what I'm going to get if I'm going to have the multiplication. Now, using this, I need to implement a simple multiplier. So how I'm going to implement a multiplier? So for this, I'm going to take one AND gate. So this AND gate, I'm going to take A0 and B0 so that I'm going to get the product term, that is A0 and B0. This is the product term I'm going to get. Now over here, for getting A1 B0, I'm going to take this B0 as one of its input and A1 as one of its input so that I'm going to get over here A1 B0. This is one product term. And for getting this product term A0 B1, so I'm going to take one more AND gate like this where I'm going to take A0 is already present. So I'm going to take the same A0 and B1. So I'm going to take one more input as B1. And here I'm going to get A0 and B1. So using the AND gates, I can implement them. And I'm going to take A1, B1, A1 and B1. So from here, I'm going to get A1 and B1. So these are the product terms which I've got. Now what I'm going to do, so this product term is directly given to your output that I'm going to give directly to my output, and this is nothing but my first term. Let's say this is M0. This is my first term. Now for getting this S1, what you're going to do, you need to add this two terms. So I'm going to take this and this term and I'm going to give it to a half adder. So this half adder is going to add these two terms and it is going to give me S1. This is my S1. And C1 generated will be given to second half adder. So I'm going to have one more half adder like this. This half adder is going to add this carry with this particular product term so that I'm going to get another term S2. And this is my output carry C2. Okay. So I've got S2 and whatever the carry which will be generated that will be given over here. So this is how I'm going to implement a multiplier using the logic gates. Okay. Yes. Is it clear? Any doubts or any queries over here? So is this particular multiplier circuit, is it clear? Any doubts or any queries? And you can also go with 3-bit and 4-bit with the same approach and you can come up with your circuit, right? Yes. Now coming to comparators. So Let's see about something known as comparator. First, let us discuss about two-bit comparator. So comparators are basic combinational circuits which are used to compare bits. Okay. So in the case of my two-bit comparator, I'm going to compare two bits. For example, if I want to compare A and B, where A is of two bits, A1 and A0, and B is of also two bits, B1 and B0. So if I want to compare these two bits, I can use a simple comparator, which is nothing but my two-bit comparator. Now, over here, my comparator, this particular circuit, let me first of all draw a black box. This comparator, it is going to have inputs as A and B, where A is of basically 2 bits and B is of basically 2 bits. And it can compare, if let's say A is greater than B, then I'm going to have a signal for representing that particular condition if A is greater than B. Okay. And let's say if A equal to B, I can use a signal which is known as equal for representing this particular condition. And if A is less than B, then I can use a condition which is known as LT. So like this, I can basically represent multiple conditions. Let's say suppose if you want to have greater than equal to 1, when B is greater than A, you can model like that. It's not a issue. You can model how many times you're going to have, you can model like that. Okay. Like let's say suppose if you want to have if your B is less than A. One second, I got a comment on YT Live. So already asynchronous before is present. Once you can now check it out in the channel itself, right? Yeah. So coming back to this particular discussion, let's say suppose if you want to model B less than A, if it is B less than A, uh, or if you want to model B greater than A and then your greater than wants to become 1, you can model like that also. It depends upon your design. Okay. Now, so I'm considering these considerations and I'm going to have A, which is A1 and A0, and B, which is B1 and B0. And here I'm going to have greater than, equal to, and less than. Okay. So these are the signals. This is my truth table which I'm going to come up with. And so have basically 16 number of combinations 0, 0, 0, 0, 0, 0, 1, 0, 1. So like this, I will have total 60 number of combinations that you can fill it out. I'm just giving you one basic idea how to come up with these equations and all. So here obviously A is less than B. So this will be equal to 0. This will be equal to 0. All these particular cases, this will be equal to 0 only. Okay. And here it will be equal to 1. For this particular case, it will be equal to 1. Okay. And the remaining cases, it will be equal to 0 only. And equal to this will be equal to 1, and this will be equal to 0, this will be equal to 0, 0, 0, and 0. Okay. And less than, it will be equal to 0, 1, 1, 1, 0, and this is equal to 1. And here it will be equal to 0. So like this, we need to write down all the particular possible combinations and we need to come up with the minterms. Okay, from the minterms, we can come up with the logic diagram. Okay, so this is how we are going to come up with any particular combination circuit. If you want to design any particular combination circuit, one step you need to do is you need to come up with a truth table. If you can come up with a truth table, many of the problems you can solve it. If you can properly come up with a truth table, then using that particular truth table, you can come up with the minterms and you can come up with the expressions if you want to build up any particular combination circuit. Okay. Yes, please give it a try and fill the whole truth table and let me know what is the equations you're going to get for your 2-bit comparator. Okay. Yes. So this was about my multiplier and 2-bit comparator. Okay. Now let's start with the discussion of multiplexers. Any idea where are we using this multiplexers? Anyone, any idea where are we using this particular multiplexers? Like, what is the use case of this multiplexer? Where can we use them? Anyone wants to answer? What signals? Let's say suppose if I have multiple devices, like let's say suppose if I have two devices, but there is only a single bus. Okay. Like this, if I'm going to have two devices trying to access a single bus, then I can basically think of using a multiplexer over here. So this multiplexer is basically going to multiplex your input signals, and it is going to, yes, it is going to have kind of a path selection logic. Multiplexer is kind of a path selection logic, and this particular circuit is going to decide which particular device, whether device D1 or whether device D2 is going to get the access to this main particular bus. Okay, this is where we can think of using a multiplexer. So a particular multiplexer is a kind of combinational circuit which converts your 2 power n inputs into only one output. And we are going to have something known as n select lines. We are going to have total n number of select lines. Okay. For example, if my n is equal to 1, I'm going to have simple 2 cross 1 multiplexer. This is my 2 cross 1 multiplexer, and how it is going to look like. So this is my 2 cross 1 multiplexer which I'm going to have, where I'm going to have one select line and two input lines. Let's label them as I0 and I1, and this is my select line S, and this is my output Y. Okay. So this is how my 2 cross 1 mux is going to look like. And coming to this truth table, let's say if this is my select line S, and this is my input I0, I1, and this is my output Y. So I have total 8 number of combinations over here: 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So over here, I'm going to basically get y is equal to 0, because select line, if it is equal to 0, you're going to select your I0. This is my I0 which is being selected. If your select line, if it is equal to 0, you're going to select your I0 to your out. And let's say here also, if your select line is equal to 0, again you're going to select your I0 to your output. And here also my output will become 1. And here, if your select line is equal to 0, your y will be equal to 1. Okay. And here it will be equal to 1 again. This is I0 and this is 0. I'm selecting I1. If my select line is equal to 1, then I'm going to select my I1 to my out. Okay. And over here it is 0 again. Sorry, it is 1, which is nothing but my I1. And here also I'm going to have 0, which is nothing but my I1, and this is equal to 1, which is nothing but my I1. Okay. So depending upon my select lines, I'm going to decide which particular input should be given to my output. So over here in this case, I'm going to give 0, 0, 1, 1, and in this case 0, 1, 0. Okay. Now using this, can anyone come up with the equation for output y? Using this particular truth table, can anyone come up with the equation for y? Simple question you're going to have. Waiting for your responses. Using the truth table, can anyone come up with the equation of output y? Is a question. Okay, so let me write it down. So what are the minterms I'm going to have for y? So y is basically having here, I can see my output y is equal to 1. So I'm going to have s bar, I0, I1 bar. S bar, I0, and I'm going to have I1 bar plus this minterm also I'm going to consider. S bar, I0, I1. S bar, I0, and I1. And next minterm I'm going to take is this, which is nothing but S I0 bar I1. S I0 bar I1 plus S I0 I1 plus S I0, I1. So this is the equation which I'm going to get from the truth table. Okay. Yeah, we can also draw the K-map also, or we can directly solve it using the equations. Any method you can use, and you can solve the equation for y. So in these two terms, if you carefully observe, if I'm going to take S bar I0 common, I'm going to cancel out with I1 plus I1 complement. Plus, if I'm going to take this two terms common, I'm going to cancel out my I1. Okay. If I'm sorry, if I'm going to take S into I1 common, then I'm going to cancel out my I0. So my final equation of my y, which is nothing but S bar into I0 plus S into I. So this is the final equation which I'm going to get as my output of my equation. Okay, give me 1 second. Yes. So this is the equation which I'm going to get, which is y is equal to S bar into I0 plus S into I1. So this is also known as Shannon's expression. Okay. Yes. Is it clear, guys? Any doubts or any queries? And give me 1 second. So this is also known as Shannon's expression. Okay, this is also the equation of a 2 cross 1 multiplexer. Okay, so you can also substitute the values over here. Let's say suppose if your S is equal to 0, then you're going to have Y is equal to I naught. And let's say suppose if S is equal to 1, you're going to get Y is equal to I1. From this equation also you can cross verify, or else you can cross verify from the truth table. So see, if you are working with any combinational circuit, if you want to come up with a particular logic diagram or some kind of output equation, the best way is not to remember anything, just come up with a truth table and derive everything, you're going to get it. Okay. Yeah. Now, and if I want to come up with a logic diagram of this 2 cross 1 multiplexer, this is going to look like this. This is my select line and its complement. This is nothing but my S complement. And here I'm going to have I0 and this is my I1. So I'm going to have Y is equal to S complement into I0. S complement into I0 I'm going to take, and OR operation with this I'm going to make AND operation, and next I1 into S, and I'm going to perform the OR operation. This is my output Y. So this is a simple logic diagram of a 2 cross 1 multiplexer. Okay. Yes. Now, let's say suppose if I want to come up with a 4 cross 1 ones. So this was all about 2 cross 1 multiplexer. So this is how we are going to, according to the functionality, we are going to come up with the truth table, and from the truth table, we are going to come up with the equations, and from the equations, we are going to come up with the logic diagram and all. Right? Yes, yes, we will discuss everything. Yeah. First, let's discuss the basics, because if there are some people who don't know about this particular basics, and if we are jumping into those particular concepts, it will be difficult, right? Okay. Now, let's say suppose in the case of my 4 cross 1 multiplexer, and this is how it is going to look like, where I'm going to have four inputs and one output. This is I0, I1, I2, and I3. And this is my output Y. And coming to a simple 4 cross 1 multiplexer, how it is going to look like. So it is going to have two select lines. How I'm going to select it. So it is basically 2 power 2 cross 1. So this is nothing but my select lines I'm going to have. Now, so depending upon my select line, if my select line, if it is equal to 0, 0, then my y will be equal to I0, and 0, 1, my y will be equal to I1, 1, 0, I2, 1, 1, it will be equal to I3. Okay. So you can take any multiplexer. If you can take value of n is equal to 3, 4, 5, depending upon the value of n, you're going to decide what kind of multiplexer you're going to get. Okay. Now, so this was introduction to multiplex. Now, what kind of questions you can expect from this particular multiplexer is the very next question. So what is the questions we are going to discuss in this particular multiplexer is, first one is implementing all the logic gates using multiplexers. This is the first type of questions which we are going to look into. Okay, all the logic gates we are going to look into using multiplexers. And here also we have two methods for implementing it, and we are going to use a second method. I will show you all the two methods which are present for implementing this particular logic gates using multiplexer. Okay. Now, second type of question is implementing flip-flops using multiplexers. Anyways, we haven't discussed about flip-flops yet, so I'm not going to touch this concept now. Okay. Now, the third type of questions you can expect is what is this? Yeah, higher order multiplexers using lower order multiplexers. Using lower order. Okay. For example, like implementing 4 cross 1 using 2 cross 1. And someone has asked, right, 10 cross 1 using 5 cross 1. 10 cross 1 using 5 cross 1. All the possible combinations we will try to discuss. Okay, if you're having any particular queries like this, 6 cross 1 using 3 cross 1, and what else? 10 cross 1 using 3 cross 10 cross 1 using 3 cross. So this concepts we are going to look into. Okay. So these are the different kind of questions we are going to look into. And after this, fourth category of questions, what we are going to look is we are going to discuss as previously we have discussed in number systems and logic gates and K-maps, we had a kind of questionnaire discussion, right? So here also I'm going to have some set of problems that we will discuss over here. Numericals. Okay. This is what the pattern of questions which we are going to discuss, and we are going to wrap up this particular multiplexer so that if you're in your interviews, if you face this kind of questions, you will be comfortable to answering this. Okay, generally this kind of questions you will be facing in your round one interviews only. So there the main factor is time, so you need to complete or you need to answer the questions within the given time. Okay. Yes. So that's about this particular session. If you have any doubts or any of the queries you wanted to discuss with me, you can stay and discuss, or else we can wrap up the session. Okay. Thank you.